Now what we want to do is we want to look at the shapes of the orbitals. Why is the s orbital, why is that a sphere? Why is the p orbital, why does it look the way it does, as well as the d and f? We said previously that the square of the wave function, i.e. the orbital, so if we take psi and we square it, it gives the probability, remember again that word, probability, of finding the electron within a specific region of space. Now, because since wave functions, or orbitals, same thing, are waves, we must first understand this thing called standing waves. So let's talk about standing waves next. Standing wave. A standing wave is a wave between two set locations that reflects back on itself and amplifies. Let's look at this first figure here. Here we have a set location, one over here, and let's say like a wall on the other side. So a wave will first initially start out and it will just kind of be really small and it hits this point. When it hits that point, it's going to get reflected back. Okay, so it goes back. It hits this wall and it gets reflected back. Now over time, it's going to amplify, it's going to get bigger and bigger until it eventually reaches that max point here. Now remember, the reason why we're looking at standing waves is because electrons have a wave-like nature. Their wave nature is reflected by these things known as standing waves. Now we can have multiple types of standing waves. We can have this first one. Here we only have kind of one hump. Here at the second one to the right, we kind of have a one trough and one crest. Okay, and then here you can see that the wavelengths they're getting bigger and bigger. We can think of them as a rope fixed at one end and then it's allowed to vibrate. So let's say you tie a rope to a wall and you just move it back and forth. That would be an example of a standing wave. Now only wavelengths of light that are symmetrical between the two set points can form a standing wave. All others will cancel out. There are multiple parts to a standing wave. The first part of a standing wave is what is known as a node. A node is a region where a wave has zero amplitude. Let's label where the nodes are on the figure below. So a node has zero amplitude. That gray dashed line is showing where there's zero amplitude. That means you have a node right there. It has no height to it, in a sense. You have another node here and another node there. So in this wave, you have a total of 3 nodes. The second part of a standing wave is what is known as phases. These are the crests above the zero line and the troughs below. And they are represented by the algebraic signs positive and negative. So on the top of the dashed line, you have the positive phase. That means these humps are positive. And then you have the phases which are below the dashed line. We denote with the negative sign. So these would be a negative phase. So the humps below are the negative phases. Now our goal is to really understand where the shapes of orbitals are coming from. So we want to understand why does the 1s orbital, why does it look like a sphere? We said that they're based off of the standing wave. So now let's relate a standing wave to the shape. The standing wave of a 1s orbital has no nodes and is all positive. Here would be an example of this. Now, just as a review, so you can keep following along, the reason why we're looking at standing waves is because electrons have wave-like properties associated with them. Because you cannot tell where an electron is due to the Heisenberg uncertainty principle, we have to look at the probability of finding an electron. If we understand the wave-like nature of electrons, we can see where the probability is coming from. So we have to look at these standing waves. For the 1s orbital, the standing wave is going to look like the figure here. Notice we're only going to be looking at that black top line here. So all we have is the positive phase. And if I wanted to add in my dashed lines, I could. This is the area where it has 0 amplitude. So for a 1s orbital, it has no nodes associated with it and is all positive. If we take the square of this wave, remember, if you take the square of an orbital, you get the probability of finding an electron in that region. So if we take the square of this wave, it will give us the s orbital, which is a sphere. It contains one positive lobe. Okay, so can you see where we get a circle? You're basically squaring kind of the standing wave. And this entire lobe is going to be positive. Because we have a positive phase. So remember that the s orbital, it doesn't tell us exactly where the electrons are going to be found. These are going to be the most probable area where an electron will be found. So an electron, it could be found here, it could be found here. I mean, sometimes it could even be found here because the area that I circled in blue is just the most probable. It doesn't necessarily have to be there, it's just more than likely it's going to be found there. So you can find an electron here, 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 something like that. Now let's look at the 2s orbital and look at the standing wave associated with that. The standing wave of a 2s orbital has one node. An electron can never be found at a node, so it has a 0% probability. Where is the node? The node is going to be right here. Okay, and then we also have a positive and a negative area associated with this. We have the positive phase. So the positive phase is going to be right here. The negative phase is going to be on the bottom here. So the negative phase will be over on this trough. If we take the square of this wave, it will give us the 2s orbital. Okay, let's talk about what this figure represents. Okay, the area in blue, right here, this is coming from the region that has the positive amplitude. So that's coming from right here. If we take the square of that, that gives us the positive sphere. Okay, and then we have a node. This white area right in here, this is our node. And it's between the positive and the negative lobe. Okay, this is an area where no electrons will be found. And the reason why is because there's 0% probability of finding it there. Okay, and then we have our negative lobe. The negative lobe is this kind of reddish circle right there. That is coming from this negative part of the standing wave. Okay, now s orbitals in higher shells will be larger and will extend farther from the nucleus. If I look at an example, we have a 1s, let's say pretty small. If I look at the next shell, which will be the second shell, the orbital in there, which will be the 2s, will be larger. If I look at the third shell contains a 3s, and that's going to be larger still. Now the p orbital. As we're moving on, they're going to get more challenging, so we're not going to use the standing wave because that's outside of this course. But p orbitals are dumbbell shaped, and they are going to contain one node. Looking at these three figures, where would the node be located? The node is going to be right in between. Remember, the node is where an electron will not be found. No electrons will be found in that region. Okay, if I looked at the py orbital, where would the node be? Right in the middle there. And then if I looked at the px orbital, where would the node be? Kind of right in the middle again. Now there are two lobes associated with the p orbital, and they will have the different phases. You have the positive phase and negative phase. The blue is representing the positive phase. The red, or the pinkish red color, that is denoting the negative phase. Now the reason why we pay attention to the positive and negative phases is that these phases are crucial in bonding because only lobes of the same phase can interact in forming covalent bonds. That means, let's say if I take two p orbitals and we have one positive phase here, and a negative phase, there will be no bonding. However, if you can do the two orbitals where they're in the same phase, you will get bonding. So for example, if you have positive, negative, this will have bonding. Now p orbitals in higher shells will be larger and will extend farther from the nucleus, just like the s orbital. The d orbital. 4 of the d orbitals are shaped like a clover leaf, and the 5th orbital is shaped like an elongated dumbbell inside a donut. So the 5th one is just kind of an odd one. There are a total of 2 nodes, and remember, the nodes are where electrons cannot be found. Where would the nodes be located? What you have to do is kind of think of a sheet of paper. So you would have one node right along this axis. You would have a second node when you kind of cut it in half here. So you have a total of 2 nodes. With the d orbital, again, you don't need to draw them, but you need to be able to recognize that this is a d orbital. You should also be able to recognize how many nodes a d orbital will have. You should be able to recognize an s orbital, how many nodes that it has, a p orbital, d orbital, and now let's look at an f orbital. Oh, and I should mention before I move on that the d orbital will have 4 lobes. You have 2 positives and 2 negatives. So you have a positive node here and a positive node there. Negative, negative. Okay, now let's talk about the f orbital. There are 7 orbitals and they are much more complex. These are very kind of strange looking ones. You have a total of 3 nodes. Okay, now can you see where the 3 nodes are? Don't look at the first one because that one is fairly challenging to see. Let's look at, let's say this one. How many nodes do you think are there? Okay, now think of a piece of paper just cutting right through them. Okay, so if you cut right through here, you have 1 node. Where's another place you could cut through? You could cut through right here. Is there another area you could cut through? Yes. Now, it's a little hard for me to draw it, but think of a sheet of paper coming straight down here. So you can cut it right through here, all the way down. So you have another node here. Therefore, you have a total of 3 nodes. You should be able to draw this, or at least tell me how many nodes there are. And when I say draw it, you should be able to draw where the nodes are. There are 8 total lobes. You're going to have some positive nodes in there and some negative lobes as well. Let's look at this one to look at the lobes. The other ones are kind of harder to see. The red you have are your, let's say, positive nodes. So positive, 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 and then you have a red way in the back. So you have a total of 4 positive lobes. And then for negatives, you also will have a total of 4 negative lobes.